All right, it's 7:30 here. Let's get rolling. Welcome to the third topic of our MSA breakfast. It is breakfast time here, and it's not the case in all of the locations you are connecting from, but let's have a morning coffee anyway. This is the list of topics that we will be pursuing in our webinars. Topic 3 is a Metrologic trailer. We'll be talking about uncertainties type B, which for some reason tends to scare many of the people working with the uncertainties. And I would like to encourage you to send us your comments, to give us your feedback, but most of all, give us your questions into the Q&A functionality of the Zoom application, and we'll be addressing those on the go. We'll be addressing those by the end of this webinar or before the next webinar comes. All right. I'll start sharing my favorite whiteboard. So today we'll be talking about uncertainties type B. But what is very important to mention right in the beginning, that we'll be addressing the measurement system itself. We'll be only talking about the uncertainties that affect the measurement system, not the whole measurement process. So what are these? This is the list which is generally being used by the standardized methods, and this is not at all to say that these are the only uncertainties that matter, but have this as a list that reminds you of all the parts that you at least needs to think about. And if you'll find out that some of these are irrelevant for your process, for your measuring system, then you can omit them. You can assume they are zero. So a little reminder, what is a type A and type B uncertainty? Type A is anything what comes from an experiment, and this is what we talked about the last time. And type B is anything else. It is a knowledge which comes from other sources. It may be that type B would be uncertainty that you made an experiment for in a separate process, on a different measuring device, and you would like to use that knowledge acquired in the past on the measuring system that you have in hand right now, and that would be the type B. All right, there are 5 uncertainties which are being addressed by name, and that is the resolution of the measuring system, the calibration error, that is how bad what was the measuring device used to calibrate the one we are having right now, then repeatability on a reference, which in ideal case is a repeatability on a part that is almost perfect, in the sense that the part itself does not contribute to uncertainty. Then the bias, which is how off the measuring system is in a systematic way. And linearity. The linearity is a deviation along the measuring scale, which can be eliminated by putting in a formula for a line. And I'll be talking about this towards the end. And the unnamed one, the sixth one, is anything else that you can think of. And there can be multiple of these. The fives which I've named are for more or less standard measuring devices. They are almost always present. But keep in mind that in special cases, and yours may be one of those, you will need to add more uncertainties which are not directly named here. All right, one quite important thing. If you have what's called the MPE, maximal permissible error of your device, it should be a number, it should be the uncertainty that covers everything about the measuring system. So if your device comes with the MPE, which is true mostly for the standard measuring devices, like a caliper, then you don't need to worry about those and just fly with this number. And the third note I have here is on how these uncertainties are treated, how they are calculated with. And it's all given by this little green formula down here. And not surprisingly, they are treated as a standard deviation of a normal distribution. So the total, the UMS, the standard uncertainty of the measuring device, is a square root of a sum of squares of any uncertainties that come in. The only thing we care about where we deviate from this rule is if there are two or more uncertainties correlated. And we'll speak about that in the measuring process uncertainties. In the measuring system, we'll just assume they are not correlated unless we have very good reasons to think so. So what does this square root of squares, of sum of squares, actually mean? It can be thought of as a sum of vectors, as it is in this picture. So you take the first one, let's say the linearity down here, and you make a perpendicular vector of the size of bias, and you have a right-angled triangle. And the vector sum of those, if they are perpendicular, is the square root of the sum of squares. And you can be adding those one by one, always perpendicular to the last one which you had, and the total is the UMS, the uncertainty of the measuring system. So this goes in a kind of a spiral, but if you sort them from the largest to the smallest, the spiral radius will be increasing really slowly. You can see that the before I would add the U calibration, which is up there, the size of the total does not change almost at all. So this is a nice thing about uncertainties. You really need to care about the big one. The small ones are negligible mostly because of the way we are calculating with them. And that's given by this very formula. Okay, there is usually a trouble with how to fill these in a standardized software. What the calculation, what the software actually means is the standard uncertainty. And not surprisingly, it is the same, very similar thing as the standard deviation in a normal distribution. But we usually don't have the standard uncertainty. We have some other representation, and we treat it as such. We know something, that the representation we have, and we assume that this something actually is a multiple of some constant, k, and the uncertainty that we need. So if we need to take the uncertainty out, we just divide the something that we know by k. So what is something? Quite often, we will get what's so-called an expanded uncertainty. This is mostly in calibration reports, and this is the type of reports which reads somewhere the uncertainty given here was multiplied by 2 because it approximately has a coverage of 95% probability. So besides that capital U, that expanded uncertainty, you will get the K, the expansion factor, usually written somewhere in the report. So you would go with the coverage factor, or you would go with what is written there, and you will have the constant. So that's one very prominent case, and absolute majority of calibration reports has this 95% coverage, which corresponds to K equal 2. The other case would be uniform distribution. And this is the uniform distribution is assumed in quantities like linearity or bias, or even we'll be in the realm of measuring process uncertainties, it would be the shape variation of the part. They are assumed to have a uniform distribution with a center at 0. And if this is the case, then the coverage factor would be a square root of 3. And it is as simple as that, because if you want to approximate in a series of calculation the uniform distribution by a normal, then K equals square root of 3 is the exact ratio between the standard uncertainty of that normal distribution and half of the width of the uniform distribution. Keep in mind that this is half. Usually it doesn't matter. The only point where this is different is the resolution. If you think of the resolution of the measuring device, let's say 1 millimeter, it is the full length of this uniform distribution, not the half length of this. All right, I will now give floor to Martin Motička, who will show you how this is done in Yarvin, how these uncertainties are inserted in Yarvin. Martin, please go ahead.
Good morning, and I will start with uncertainty from resolution, because this uncertainty is a little bit different, because the uncertainty from resolution is the, let's say, property of the measurement system. So of the measurement system. So the only thing you need to do is to fill the resolution of the measurement system. In here I have 0.01 for some standard caliper, and the uncertainty from resolution is calculated directly from this value. So it's not necessary to add the uncertainty of resolution separately to the system. It's calculated directly from the resolution. And about the other types of uncertainties, it depends how the experiment you have is set up. And there are basically two options how to do this. First one, if you will have an experiment, and second, if you have no experiment. And I will start with this second option, that there is no experiment. And it means you can get your uncertainties by two ways. first one is something called MPE, maximal permissible error. As it was said that this MPE is some kind of maximal error that is caused by usage this specific measuring system. And this MPE, there can be more of them for some, let's say, a little bit complex systems. So you can add all of the MPEs you have. And the overall, then the overall uncertainty is calculated from the combination of all of them. So this is the first way. You have MPE, maximum permissible error. You fill this in, and the uncertainty from measuring system is calculated directly from this value, and nothing else is needed. And the second way is to make an assumption about the B-type uncertainties. Also, there is no experiment, and you can fill all the uncertainties you have. In my case, are the basic ones. As I said before, the resolution, uncertainty from resolution is calculated automatically, and you can fill the repeatability on the master, uncertainty from bias, uncertainty from linearity, uncertainties from calibration of all of your masters, and some uncertainty that you can define by yourself. For example, temperature. So this is the second way. You have no MPE, but you can make an assumption about B-type uncertainties. And the last and most common way is if you are doing some experiment. When you have experiment, it was said that some uncertainties are type A. That means that are calculated directly from the data, and some of them are type B. That means these uncertainties are filled manually. Type A uncertainties always be bias, it always be repeatability. Type B always is uncertainty from resolution, calibrations of the masters, and the other uncertainties you will use and you will define by yourself. And what is left here is linearity, because the linearity, how it's calculated, it depends how many masters you have. I will start with this case. I have only one master, and if you have only one master, it means you cannot calculate from the data the linearity. So in this case, it means that linearity is B-type uncertainty. You can fill it as B-type and work with this information. A little bit special case is if you have exactly two masters, because if you have two masters, you can calculate linearity from the data, but the bias is 0. And why the bias is 0? This topic, I think, will be discussed in some of the next episodes of our breakfasts. So if you have two masters, it means that linearity is type A, and the bias is 0. And if you go to the B-type section, you can see that there is no linearity because it's calculated from the data. And the last option is if you have more than 2 masters. In this case, for example, I have 4 of them, and the B-type uncertainties also, you can see that linearity is gone. It's calculated from the data. It's type A. Bias will be also calculated from the data, also type A. And in here, in the B types, is only the other uncertainty and calibrations for the masters. So this is how the situation of B types looks like depending on the setup of the experiment, if you are doing an experiment or not, and how many masters you have. And how to fill the uncertainties. As Jaroslav said, it is always it is some value and some coverage factor. And the value can be defined by 2 ways in the most cases. First way is that the value you have here, for example, something like this, is some kind of uncertainty. If this value represents the uncertainty, the coverage factor then will be 1 or 2, and in some special cases it can be something different. The coverage factor of 1 means that this value is standard uncertainty. If you use coverage factor of 2, it means that this value you have here is expanded uncertainty. And the second way how you can do this is if you have some kind of error that is caused by this specific effect. And in this case, the coverage factor is defined according to the distribution that is assumed for this effect. And we have the most common distributions: U distribution, coverage factor square root of 2, uniform distribution, coverage factor square root of 3, and triangular distribution for coverage factor square root of 6. So this is the way how you can fill the B-type uncertainties. Always some value and coverage factor. And the coverage factor depends what the value represents. If it represents uncertainties or some kind of error that is caused by this specific effect. So this is everything I want to show you, and I will pass the word back to Jaroslav.
Thank you very much. The last part I want to cover is what it actually means. What are the details of this to be filled in? One of the reasons people fear of filling this in is that not always it is clear what it represents. I would like to show you that you can actually make an educated guess on many of these if there is a mutual understanding of what these actually are. So I'll try to make a little picture on this. Let's say that the measuring system here is trying to estimate the reality. So in ideal case, if the measuring system shows exactly what is the linearity, it would show the value on the black line in the center. This line over here. So whatever comes in gets exactly the precise value coming out. But that is not the case, as you can imagine. So if whatever comes in is burdened by the error of the calibration. That is the first one. So the reality, you can think of the calibration of something what burdens the reality itself. Then the second question is how this gets treated. And as I've said, there are three. The linearity is anything what can be straightened, what can be compensated by a line. And that's represented by this green line, thick green line in the center. You can eliminate that error by putting this line on the black one. Then, of course, not everything can be eliminated by linearity. So we have the bias. So the deviation from what's compensated on the line would be the bias. And in these cases, we would go for the extreme. So the biggest deviation of this thin green line from the thick green line would be the bias. And then, of course, we cannot compensate by some prescription, by some formula in the measuring devices, because there always is a random error. And the random error would be the area around this thin green line, and we care for the thickness of that area, for the broadness of that area, represented by the equipment variation, the EV. So let's think of it this way. If there is some real value like this, it is already being offset by the calibration error to some degree. And the this value gets translated into the measuring system, where first it hits the random error, the belt, so it randomly chooses the value from this belt, and this belt is deviated by the bias from something what can be compensated by a line. Then it hits the line. Please note that the linearity is an extreme value on the edge of a tolerance, and it is always on the edge of a tolerance because it is a line. It can be the left one or the right one, but it will be the maximum on one of the two of these places. And then when this value gets out, it will hit the resolution. From the measuring device, you cannot get the continuous value. You will only get the discrete values per the resolution. So that would be the last deviation covered here. So don't be scared of this. Just think of what can come in and what will get out, and try to wrap your mind into this. And with a little bit of technical expertise, with a little bit of knowledge of what is inside of the measuring device, you will be able to at least approximately estimate what is the size of these uncertainties, how big they are. And this is what matters. If you cover the biggest one, as I've shown you, because of this vector sum, you will be fine. You don't need to care about the little ones. If you are not sure, try to be a little bit conservative. If you will say it is bigger than the reality and the measuring device will still pass, it still would be capable, that's completely all right. You don't need to worry about that. Okay, so that's all for today. Looking at Q&A, I don't think we have anything today. Is that right?
Yes, there are no questions.
So if you will have any questions, please let us know. You can reach us on the emails given in the invite for this for this webinar, and we are very much looking forward to see you next time. And that's all from us. Have a nice day.
Deary bet, we are deary bet. Deary bet, we are deary bet. Deary bet, we are deary bet. We are deary bet.